Welcome to the Explainer. Today, we're jumping right in to decode the absolute ultimate tools of electrical circuit analysis. If you've ever looked at a messy, tangled schematic of an electronic device and wondered how anyone could possibly make sense of the whole shebang, well, you're in exactly the right place. So, focus in and let's get ready to decipher the fundamental rules that govern the flow of electricity. So, how exactly do you solve the unsolvable? Picture this. You've got a really complex circuit. We're talking multiple intersecting wires, several batteries scattered all over the place, and a whole bunch of resistors woven together in this crazy grid. You try throwing basic Ohm's law at it, but you quickly realize you're totally stuck. There's no simple series or parallel combination to shrink the circuit down. It looks, quite frankly, entirely impossible to figure out how much current is actually flowing where. Section 1. The complex circuit puzzle. Think of this whole thing like a detective story. We're standing right at the scene of this complex circuit puzzle, and we need a very special set of rules to untangle this impossible web. But before we crack the code, let's lay the absolute groundwork. We need a clear vocabulary so we don't get completely lost later on. First up, we have a node. This is just a junction where multiple elements or wires connect together. Next is a branch. Think of this as a single electrical element's path, like a resistor or a battery sitting directly between two of those nodes. And finally, we've got a loop. A loop is any closed path within the circuit where you start at one node, trace a path through the branches, and come back to your exact starting point without visiting any single node twice. Make sense? Node, branch, loop. Those are our basic building blocks. Section 2. Gustav Kirchhoff's Historic Discoveries. Let's meet the brilliant mastermind who actually cracked this code for us over a century ago. His name was Gustav Robert Kirchhoff. Born in Prussia back in 1824, he went on to become a totally legendary physicist. His early research was all about the conduction of electricity, and honestly, the most incredibly impressive part? By 1845, when he was just 21 years old, he formulated the exact laws of closed electric circuits we're digging into today. That 1845 formulation gave us the precise mathematical tools we need to solve literally any circuit. He even went on to become the first person to verify that an electrical impulse travels at the speed of light, plus he made massive contributions to spectroscopy. But today, our focus is entirely on those game-changing circuit laws. Section 3. The current junction rule. Okay, let's grab our first detective tool, Kirchhoff's current law. You'll usually hear this called KCL, or simply the junction rule. It goes like this. Total current in equals total current out. It's incredibly straightforward. Imagine water flowing through a bunch of plumbing pipes. If you have 3 gallons of water entering a pipe junction every single minute, you absolutely must have exactly 3 gallons leaving that junction every minute. If not, well, the pipe bursts. In an electrical circuit, it's the exact same logic. If 3 amps and 7 amps enter a node from 2 separate wires, exactly 10 amps must be leaving it through the remaining wires. The total sum of the currents entering a junction will always equal the sum of the currents leaving it. And you know, this points to a much deeper truth about our universe. The quote goes, "The algebraic sum of every current entering and leaving the node has to be null." This property is commonly called conservation of charge. That is the profound why behind this simple equation. Charge can't just magically be created out of nowhere, right? And it can't be destroyed at a junction. Whatever electrons flow in absolutely must flow out. It's a fundamental principle of physics practically applied to solve our electrical problems. Section 4. The voltage loop rule. Now we're shifting gears. We're moving our focus away from the junctions and expanding our view to look at the entire closed paths of the circuit. This is Kirchhoff's voltage law, or KVL. The sum of voltages in a closed loop equals 0. Think of it kind of like a hiker walking a mountain trail. If you start at a specific base camp, hike up some crazy steep hills, drop down into some deep valleys, and eventually return to your exact starting base camp, your net change in elevation is perfectly 0. You're right back where you started. In a circuit, as you conceptually walk around any closed loop, the voltage drops across the resistors, and the voltage lifts from the batteries must perfectly cancel each other out to 0 by the time you complete that circle. Side by side, these two concepts are just beautifully balanced. On one hand, we have KCL, the current law. It deals strictly with current at a junction, and it's securely rooted in the conservation of charge. On the other hand, we have KVL, the voltage law. It deals with voltage around a closed loop, and it is firmly based on the conservation of energy. Because voltage is fundamentally a measure of energy per unit charge, Walking a full loop and arriving back at your starting point means no energy was lost or gained overall in that closed path. These are your twin pillars of circuit analysis. Section 5. Mastering the sign convention. All right, we know the laws, but here is where we literally have to be precise. Let's drill down into the resistor rules. When you apply KVL, you pick a loop and conceptually walk around the circuit. Now, pay super close attention to your path compared to the current. When your walking path goes in the exact same direction as the current flowing through a resistor, you experience a voltage drop. So in your equation, you write that as a negative value, minus I times R. But if you walk in the opposite direction, like swimming upstream or walking up a hill against the flow of the current, you experience a voltage lift. So you write it as a positive value, plus I times R. Just remember, moving with current is a drop, moving against current is a lift. Now, what about batteries? Well, they're actually even simpler, because for batteries, the current direction doesn't matter at all. Only your walking path does. If your loop's path takes you from the negative terminal to the positive terminal of a battery, you are literally stepping up to a higher potential. That's a voltage lift, so boom, you give it a positive sign. Conversely, if you step from the positive terminal down to the negative terminal, that's a drop in potential, so it gets a negative sign. Moving toward positive is a lift, moving toward negative is a drop. Keep those conventions straight, and I promise you will never make a mistake. Section 6. Solving the circuit step by step. All right, we've got all our clues. Let's bring this to the finish line. We can break this intimidating algebra down into 4 simple, bite-sized steps. Step 1. Label everything. Mark your nodes, choose your loops, and just draw arrows for your current directions. And here's a huge secret. It's perfectly fine if you guess the current direction wrong. Seriously, the math will simply give you a negative answer at the end, which just tells you it actually flows the other way. Step 2. Apply KCL, the current law, to your junctions to generate your first set of equations. Step 3. Apply KVL, the voltage law, to your loops to get the rest of your equations, carefully using those sign conventions we just drilled. And finally, Step 4. Solve the resulting system of mathematical equations. Once you follow those steps, that totally impossible circuit, it transforms entirely into a simple algebraic puzzle. You'll end up with a neat system of equations. You might have equation 1 from a node and equations 2 and 3 from your loops. From there, the physics is completely done. It becomes a straightforward process of substitution or elimination to find your unknown variables, like I1, I2, and I3. You just turn the crank on the math, and it brings you right to the solution. So to wrap up this explainer, I want to leave you with a thought. How do these microscopic conservation laws impact the massive power grids that run our modern world? Well, the exact same fundamental rules that dictate the flow of electrons in a tiny circuit board on your desk are the exact same rules governing the massive interconnected power stations routing electricity to millions of homes and cities right now. Understanding Kirchhoff's laws doesn't just let you solve a tricky homework puzzle. It literally gives you the blueprint to understand the energy infrastructure of the entire world. Thanks for diving into this with me. Keep exploring, keep questioning, and I hope this leaves you eager to uncover even more about the amazing world of electronics.